I'm Brendan McBain, and this is my final year project, a library for polar coding and shortening algorithms in Python, under the supervision of Harish Vangala at Monash University. Polar codes are a state-of-the-art channel code being used in 5G and beyond, and they're the first mathematically proven capacity-achieving code. Their rise to fame in the communications community is because of their remarkably low time complexity for encoding and decoding, in conjunction with their high performance even at finite block lengths. However, conventional polar codes are restricted to block lengths with powers of 2, and applications such as EMBB in 5G requires either 64,800 bits or 1920 bits. And so we are motivated to create algorithms such as shortening and puncturing algorithms to combat this. My project is dedicated to implementing some of the most common polar coding algorithms for construction, encoding, decoding, and shortening, all in Python, and is aimed at students, designers, and researchers of polar codes who either prefer or are obligated to use Python programming for their work. My main contributions for this project is creating a polar codes Python library with encoding and decoding functions, simulation and plotting functions, support for shortening and puncturing, a few shortening algorithms, and I've also provided a user-friendly interface with the Python library. There are also two types of documentation. The first one is the main reference, which is a detailed explanation of the algorithms and their implementation, as well as a quick reference for programmers to easily learn the syntax of the library. Now let's go through the few steps that we need to take to encode and decode a polar code. The first is construction. Polar codes are based on polarization of the bit channels, which tries to combine the capacity of all the bit channels and then split them into more reliable and less reliable channels, hence the name polarization. We need algorithms to tell us how reliable each of these polarized channels are, which can be found either using the upper bound on bit error rate for each bit channel in the case of the Bhattacharya bounds, or use the mean likelihood density in the case of the Gaussian approximation. Once these polarized bit channel reliabilities are known, we can then sort them to find the indices of the n-k least reliable bits, and these are referred as the frozen bits. Encoding is relatively straightforward. Firstly, we must take a bit string of length n and set the bit indices from the frozen set to be 0, typically, and then we set the remaining bits as the message bits. And then to encode, we simply multiply this by the nth Kronecker product of Arikan's kernel, as stated here, where n is the log base 2 of the block length. And we can also represent the kernel for different block lengths using this visualization, which is often called the code tree. And we will be using this for encoding as well as decoding. And we also see in orange, this refers to one Arikan kernel. For decoding a polar code, we have a number of options for polar decoders, each trading off computation time with accuracy as they all try to find the best maximum likelihood estimate. The first polar decoder ever invented was the successive cancellation decoder, which successively decodes each bit and uses the observation of previously decoded bits to improve future decoded bit estimates. The decoding is performed by computing the likelihoods at each stage of the coding tree and then estimating what bit this corresponds to. However, the order of decoding is very important and also a reason why parallelization of this decoder is also difficult. Shortening works by not sending coded bits from a chosen shortened set, and instead assign them to a known value, say 0, that is known a priori by the decoder. And by virtue of not using these bit channels, we are losing their respective channel capacities. And so we are motivated to find algorithms for choosing the shortened set as well as the frozen set that reduce this performance deficit. However, each coded shortened bit is mapped one-to-one to a corresponding uncoded bit that's often called an overcapable bit, and clearly we want to avoid a 0 being in place of a message bit that surely will cause a frame error. And this can be defined mathematically using the shortening rule that has properties to specifically avoid this. For example, say we want to shorten bit at index 6, then its corresponding overcapable bit will be at bit index 7. We can find this mapping using either the perfect polar code construction algorithm from the library that uses Boolean algebra, or we can use density evolution with the traditional polar code construction algorithms, also from the library. And then we know which bits in the code tree must be shortened and hence their mappings. The challenges of shortening is that we need to choose the optimal combination of the frozen set jointly with the shortened set, and the solution space is exponentially large. So we often restrict this solution space, for example by forcing the one-to-one mapping to be identical, so the shortened set indices will equal the overcapable set indices. And as for the implementation, it's relatively simple. All we have to do is we can use the mother code encoder and then truncate the code. And we can also use the mother code decoder and then set the shortened bit likelihoods to infinity. This package implements 3 of the most common shortening algorithms at present time, though there currently aren't that many. But in the library we have the Wang-Lu shortening, which is the most common output of the Wang-Lu algorithm. And we also have the bit reversal shortening, BRS, which is the bit reverse indices of Wang-Lu shortening. And then we have BGL, which is an algorithm dependent on the frozen set of the mother code. So now that we've gone through construction, the encoding and decoding, as well as shortening of a polar code, now let's go through a quick overview of a real system putting this all together. So we start off with U, the information, which is k bits. We send this through the polar encoder, which gives us a code word of n bits. And then with shortening, we use our shortening algorithm to truncate this code word down to m bits. And then we modulate using BPSK and put it through an AWGN channel. And then we end up with m real valued likelihoods. And then we de-shorten by appending plus infinity for the indices of the shortening set. So we're appending, and now we have real n real values, and we give this to the mother code polar decoder using the information set, the frozen set, and the shortened set. And then we end up with our information estimate of k bits. Now let's take a look specifically at what functions are in the library. The construct class has the Bhattacharya bounds polar code construction, the Gaussian approximation polar code construction, and the so-called perfect polar code construction used in shortening. We have encode, which has a non-systematic encoder. We have decode, which has a successive cancellation decoder. We have AWGN, which has a BPSK modulator and an AWGN channel model. And finally, we have shorten, which has Wang-Lu shortening, bit reversal shortening, the Wang-Lu algorithm, and also the BGL shortening technique. The library is open source and available for free download at github.com/mcba1n/polar-codes. And here it provides a description of the library, installations for getting started, as well as examples, and of course the documentation. Here's how simple it is to encode and decode in this package. First, we must specify the polar code with n and k. Then we construct the polar code object using designer sonar. Then we set the message, myInfo. Then we encode our polar code object. Then we put the object through the channel with the design SNR, and then we decode the polar code. And then we have my info estimate at mypc.message received. Once you have successfully installed and tested the library, then we can open the graphical user interface by finding main.py and then clicking Run. Once the window opens, we have a preset for an example polar code that is ready to be simulated. But for a custom polar code, we must specify the following fields: N, the block length; K, the message length; the mother code construction; the design SNR; the maximum number of iterations per SNR value; the minimum frame errors for the stop condition for each SNR; the directory to save to, and the range of SNR values to simulate. In addition, if the block length n that you entered is a non-power of 2, we must also specify the shortening algorithm from this list of options. Also, if you wish to manually enter the frozen bits or the punctured or shortened bits, then we need to check the manual construction box here. Otherwise, it'll run using the algorithms that you told it to run with, and it will print out the frozen bits and or shortened bits depending on your code. So let's do an example. Let's simulate a block length of 98, message size of 70. Mother code construction, byte chariot bounds. Let's do a design SNR of 4 dB. Let's leave the default simulation parameters. The shortening algorithm will be bit reversal shortening. And now we're ready to simulate. Okay, so now the simulation has completed. We can see the frozen bits here, the shortened set right here, and now we're ready to plot. For plotting, we must specify our root directory where our data has been saved to, and the file names, which can be more than one if you separate them by a comma. But here we want to plot what we just simulated, PC sim. So let's plot. And there's our result. Here we have an example plot of a mother code being shortened using all the algorithms from the package. Specifically, we have a 12870 mother code that's being shortened to 9870. The x-axis is the design SNR in decibels, and the semilog y-axis is the frame error rate. Let's take a frame error rate of 10 to the minus 2 for example. The best performing shortening algorithm is BRS, which is quite typical, and it has a 1 dB margin with the mother code. Additionally, BRS is approximately 0.2 dB better than WLS and 0.4 dB better than BGL. Note that the code rate is important with regard to these margins. Reducing the frozen set size tends to bring these algorithm margins much closer together, and hence less performance gains. In addition, literature has shown that there is a crossover point between shortening and puncturing, so keep this in mind in your designs. Every project has its implementation challenges, and a few of mine include limited shortening literature, since the research is predominantly on puncturing. Second, turning the pseudocode, which is often recursive, into non-recursive implementations so that we have a speed increase. Third is numerical precision, which is using the log domain conversions for each equation in construction and decoding equations. And finally, shortening with non-finite likelihoods. This requires a lookup table in many of the log domain equations that don't behave well when we have inputs with non-finite likelihoods, such as the positive infinity we see with shortened bits. In conclusion, I hope this library will be a useful contribution to the Polar Codes community. Thank you for listening.